So I want to show you a nice and easy way to identify redox reactions. You probably have already identified many of these reactions that I have listed below in this worksheet. And many of them are redox reactions. Most reactions, in fact, are redox reactions. So I want to show you a nice, easy way to identify them. But before I do so, to give you some contrast, let's go through the traditional way of identifying a redox reaction. All right, so I'm going to start with number 1 here. And I'm going to zoom in a little bit. And in order to identify a redox reaction, of course, redox means you have reduction, which means you're gaining electrons, negative charge, and your charge is dropping, and oxidation, which is loss. So we have electrons being passed around in the reactant side, which means the product side, the atoms that have gained and lost are going to have changes in their charges. We like to say oxidation states. So the first skill you're going to get is assigning oxidation states. So I'm going to do this traditionally first and then show you the nice, easy way to do this. Okay, so in any case, let's be crazy and start in order number 1 and look at lead nitrate. All right, so a couple of things here. Number 1 is to identify the fact that assigning these charges to atoms, oxidation states, is something you probably already have done in identifying the names of some of these salts. Okay, so in any case, let's get crazy here. So we have lead, and lead we know can be +2 or +4 if you look at the reference table. So a couple of tricks here. Number 1, nitrate listed in your table E is -1, and there's 2 of them. So this is -2 overall. Lead has to be what? Well, the whole charge of this salt, this ionic compound, has to be 0. I know that because there's no charge written there. It's because all the positives and negatives have to equal out. When you've done naming of these salts or ionic compounds, you've done that. So lead is +2. All right. And because there's only one lead, the individual charge is +2. So I do individual charges on top, overall on the bottom. Now, I could assign an oxidation number to nitrogen and oxygen, but I'm not going to, and I'll explain why in a second when I get to that. All right, iodine, or potassium iodine. Now, I don't care about this coefficient. Some people get bothered by it. So the coefficient has nothing to do with the individual charges. Now, potassium, a group 1 ion, can only become +1. And kind of simple, it's +1 overall because there's only 1 there. Has to equal 0. Iodine has to be -1. And iodine's a halogen, and all halogens become -1. They're 1 away from being stable. And you can look that up in your reference table. Okay? It does have some positive oxidation states, but my friends, it's the only negative it has. So that's pretty straightforward. And then we go on to lead 2 iodide. Lead iodine can only have 1 negative oxidation state if you're looking at your reference table. So in the upper right hand corner of the Regents, New York State Regents reference table, it's -1. If you don't have that, well, you know it's 1 away. It loves to become -1 and fill the octet. Now, in truth, it does have other oxidation states, but they're all positive. Lead, as a metal, can only be positive. All right, it's really important you understand there's no metal that becomes negatively charged. All right, so if you notice, you've got what? You've got 2 iodines. They're -1 individually, -2 overall. Remember, I do the overall charge on the bottom. So this lead has to be +2 for the whole thing to equal 0. And since there's only 1 lead, it's +2. And then over here, we have potassium. When it's bonded, it can only become +1. All right. Again, don't look at the coefficient. It has nothing to do about the individual charge. The nitrate is -1, okay, for this to work. So if you look carefully at my work here, you can see that the lead being +2 is still +2. Look at the iodine. It's -1 here, and it's still -1, okay? And the potassium, +1, still +1. The nitrates are -1 collectively. And if that's confusing you that I did the charge of the nitrate, let's break out the nitrate to complete this. NO3 is -1. So because it has a charge, the bottom, the overall, like I like to do that, is equal to -1, not 0. Oxygen is -2. It's 2 spots away, or 2 electrons away from filling its octet and being like a noble gas. Or if you're in a Regents reference table, you can look at the upper right-hand corner. It becomes -2. Now, because there's 3 of them, 3 times -2 is -6. So what number plus a -6 gives me -1 plus 5? So we know that nitrogen in a nitrate, my friends, is plus 5. And because it's still a -1 altogether, we can guess that in the same nitrate, it's still plus 5. Okay? And the oxygen's -2. So nothing has changed since it's still NO3 and acting as a -1 ion. So again, what am I doing here? I'm assigning oxidation numbers because, party people, I want to see if, in fact, okay, we actually have a change in the oxidation state. Lead is +2 on this side, and it's +2 on this side. It didn't gain or lose any electrons. Its charge did not change. Nitrogen is +5 on this side, and it's +5 on this side. Okay, potassium is +1. Okay, +1. Iodine is -1 and is -1. There is no oxidation number, okay, that has changed. Oxygen is -2 in the nitrate and still -2. So we would say that this is not, or this, is it a redox reaction? No. It is not a redox reaction. What is it, though? You should recognize this to be a double replacement. Let's write that in. Okay. And there's a reason I'm doing that, because anytime we're dealing with reactions where ions are either dissociating away from their solid, it's called ionization reaction, or they're just switching partners like a double replacement, it's not a redox reaction. Okay? So that is the traditional way of looking at a redox reaction and say, hey, is this a redox reaction or not? Okay? And if the oxidation numbers, the individual ones, are not changing, no electrons are being passed around. No one's oxidizing and no one's reducing. Okay, now let's go on to the next one. Now, if we assign oxidation numbers, and again, it's the last time I do this, okay? So I'm going to assign oxidation numbers here. I want you to realize that in lead here, it's a standalone element. I tell in my class, I say atom, because elements are made of atoms. I say atom, you say neutral. Atom. Come on, say it. Atom. All right, if you didn't say it, okay, it's an atom of lead. And guess what? It's a standalone. Standalone elements are always electrically neutral, okay? Why? Because protons equal the electrons. Now, this is also an element, okay? Some courses will call this a diatomic molecule or whatever, okay? But it's an element bonded to itself. It's still an element, okay? So therefore, its group of protons, whether it be 2 atoms here, okay, or like a sulfur bonded to 8, it's going to be electrically neutral. It's a group of the same type of atoms. All the protons equal electrons. You have to recognize, party people, your standalone elements here, okay? Your standalone elements, okay? These guys are going to indicate whether you have a redox reaction or not. I'm almost done showing you, but let me just stay on task here. Okay, hard for me. Not caring about this coefficient, okay? But now in lead oxide, well, I know that oxygen can become -2. There are scenarios, very few and far between, that become -1 and even +2, but most of the time it's -2. And I think given another video, we can get into that a little bit differently. But lead must be +2 here, okay, for the whole thing to work. Now look back. Whoa, oxidation numbers are changing. Lead is becoming lead is becoming +2 here. And what does that mean? Well, that means it must have lost electrons. And oxygen is becoming -2. What does that mean? It must have gained. So, my friends, in chemistry, electrons were passed from the metal to the nonmetal. Metals lose electrons. They oxidize. So, electrons are being passed. And this is a redox reaction. But as I said, party people, there's an easy way than assigning. So, in this case, this is a redox reaction because the oxidation numbers are changing. I'm not writing any more, okay, oxidation states. So, of course, let's just write this out. This is yes. It is a redox reaction. In fact, of course, it is a synthesis reaction. And for speed purposes, we're just going to go through this. I'm going to tell you whether something is a redox reaction or not based upon this very simple identification skill. Okay, are you ready for it? I know I've been holding you back. It's a cliffhanger. Hold on tight. Here we go. Number 3. Is this a redox reaction? Now, we can do what? Assign oxidation numbers. Don't have to. Okay? Notice in number 2, reaction 2, that was a redox reaction. Let me explain the easiest way to do this now. If you have a standalone element, that means you have a 0 for this compound. When it's bonded, it has to be something other than 0. So if you see a standalone element, at least one, okay, on one side, at least one side of a reaction, you know it's a redox reaction. So do we see, and the reason why it works, I'm so sorry, the reason why it works, you have to know, is that if it's a 0 on one side, that means it's going to be bonded on another side. And when it's bonded, its oxidation state can't be 0. That means it's changing. So the easiest way to identify a redox reaction is to see that if you have any standalone elements. And number 3, there are no standalone elements. So my friends, there is not a redox reaction. How about number 4? Do you see any standalone elements? I see 2. There they are, my friends. Okay? And those are your standalones. So those are zeros, which means sodium, all right, is not a 0 on that side, which means the what? Oxidation numbers. Hydrogen's a 0 on the right side, which means when it's bonded to an oxygen in water, it's something other than a 0. Of course, it's +1. Oxidation numbers are changing. So, yes, 4 is a redox reaction. And number 5, do you see a standalone element? Yes, zinc and hydrogen. By the way, classic redox reaction, this is a single replacement. Single replacements always wind up with a standalone at the end that gets kicked out. And you start with a standalone. So single replacements are a great example of redox reactions. This is, of course, a redox reaction. You have a standalone. How about number 6? If you look at number 6, my friends in chemistry, there are no standalones. Every atom, every capital letter is bonded to another capital letter. There's no standalones. This is a double replacement, so this is not. How about number 7? Hey, this is a synthesis, but I see what? 2 standalones. 2 zeros. All you need is one atom that's hanging out by itself to know it's a redox. This is a redox reaction. How about number 8? Oh my gosh, there's the aluminum. There's the copper. Standalones. Okay? That means we have, my friends, a redox reaction. Is a 0 on one side. Aluminum is not a 0 when it's bonded. Okay? And again, this is another example of a single replacement. Now, number 9 is an example of a decomposition, but it's also a redox reaction because I've got what? Standalones. Standalones. Okay? Number 10 is a single replacement. And guess what I got? Standalones. Standalones. Number 11 is a combustion reaction, but it's also a redox reaction. Why? You said it. A standalone. Even though oxygen's bonded to itself, it's still an element bonded. So even though 11 is combustion, it's an example of a redox. Even 10, if you call it a what? Single replacement, it's a redox. Even number 9, when we call that a decomposition, a redox reaction. So if you had to guess in a FRQ, in the part 2 of the Regents or any test, a good guess would be a redox reaction. All right? And of course, number 12, don't see a redox reaction. Now, K plus is not an atom, it's an ion. So that is not a standalone, it's a standalone ion. It's important you recognize that because, hey, if I go back to my regular ink here, this is a -1 ion for a nitrate, K is +1, and it's still +1. So don't fall for the fact that you see a K, all right? So that is not a standalone. That is an ionization reaction. That's basically positives and negatives just breaking apart in water. So ionization reactions, and guess what else? Double replacements, like number 6 and number 3, even though it's a neutralization reaction, you can consider it to be double replacement, and number 1. So real easy. 4, yes, it's a redox reaction. Now, if someone asks you in an FRQ why, you would say that the oxidation numbers are changing. Don't say you've seen a standalone. Okay, but this should be pretty easy now. 5, yes, even though it's a single replacement, Okay. Oh, Christmas in July. Yeah. Sing replacement, just like number 4, it's also redox. And number 6, no. Okay, you can think of it as just the ions on one side just changing partners. It's not changing the oxidation state, so no. And of course, yes, even though that's a what? Synthesis reaction, it's also redox. You see a standalone. Oxidation numbers are changing. Number 8, of course, yes. Number 9, yes, I think you get the idea. Number 10, yes. And number 11, yes. So you can see most of the reactions that you've learned in this course, okay, and these are all the reactions in Regents chemistry, okay, except the nuclear reactions, all right, they're, with the exception of what? Ionization reactions, where you have ions breaking apart, dissolving, or double replacement. Everything else is a redox. But the easiest way to identify, do I have a standalone? Hope that helped and makes your life a lot easier. Good luck.